When I ran into my first numerical methods piece, and we did it in calculus. We didn't have a whole separate class for it. So they built everything in, and we did it all as programming. Right? There was no, Maple, MATLAB, any of that kind of stuff. We had to write all our own programs, and of course, we didn't write them in C++ because that wasn't around yet, nor was C. We had basic Pascal and Fortran that we could program in. This particular version on the left-hand side is in C++. It's an update of a C program I did a long time ago. The whole top is just comments. And then here I define something called tolerance. If you define this, what happens when it goes through and compiles this mess? It takes every occurrence of this word tolerance, replaces it with this number, and then it becomes much faster. And here, since you defined it, you just change this. If I want more accuracy, if I want 9 decimal place accuracy, I could change just this, recompile it, and I'm good to go. I have to include the math header just in case when I change the functions, I get a sine, a cosine, anything else that's funky. I predefined an fx and a dfx. The dfx is just a derivative of whatever I put in for fx. Right, for Newton-Raphson method, I have to do both. I have to be able to take that derivative and put it in. I ask for the initial guess, and then what happens is, notice these are all in double. And then I go ahead and, as long as the function that I am evaluating is greater than tolerance or it's less than negative tolerance, which means that I'm approaching it from the negative side coming towards 0, or I'm approaching it from the positive side decreasing towards 0. As long as it's one or the other of those, it will go ahead and just print the 2, do the iteration based on Newton-Raphson, and then go back and do it all again. Do the check again. Once it gets to the final and that check fails, the while loop fails, we fall down through and it prints out my initial guess and the final approximated value. In this particular case, I went x cubed plus 2x minus 1, and you take derivative of that. That's just 3x squared plus 4x, which is not a big thing. And if I run that, it tells me my build is successful. Now I'm going to put in a really crummy guess. Quite honestly, I know what the answer is, but I'm going to put in a really crummy guess. I'll put in 2. And just that fast, it spits out the answer. Notice that at 2, the function is 15. And so it gets down to 1.5, 1.25, 1 1/4 very quickly at 4. Then it shrinks to 0.8. And then we're in the 0.6s, and it's converging rather rapidly. And all of a sudden, I'm down here, and I'm times 10 to the minus 6, which is wonderful. And notice the last value is what I get. The last value, it does not appear in the list. It appears down here in the output, because now I'm down to that tolerance level, 1 times 10 to the minus 8. Right, so my answer is 0.618034 for that thing. I don't expect any of you to program, and I don't expect you to program inside something like Maple. There's a lot of root finding programs out there for Maple and MATLAB. They have built-in functions to do this. Don't write programs inside programs. Use the built-in functionality. That's why it's there. Inside this Maple worksheet, I've got to restart just so it clears all the registers, all the memory. And then I load this. I didn't put a colon next to this just so you got to see what happened. These are all the subroutines that it loads. Right, and roots is going to be one that we want. Secant, Stephenson. It does Taylor approximation and Taylor polynomials. It does all sorts of things. Just so you get to see everything that it will load. If you're using MATLAB, it will do a similar sort of thing for you. I started with the bisection method. There's 2 different calling routines to be able to get to bisection. I started with a fairly nasty function. Right? The natural log of 1 minus x. Notice you're going to get at x equal to 1, you're going to get a problem. And then cosine of 1 minus x. And then it has only one root if I graph the thing. And I always recommend that, especially with these symbolic algebra packages, if you have the chance, graph it. Graph the heck out of it. It will get you an approximation to the root. Like I can tell here it's between 0.5 and I know 1 is not possible, right? So it's got to be like between 0.5 and 0.8. And that's the range I used, and I get fairly good convergence for methods that actually work, right, and do a decent job, like this bisection method. So I go through, and if you notice here, tolerance, I put in 10 to the minus 4. I could get even higher tolerance if I want, but it's not necessary. You have to put in the function, the range for the function for bisection. I have to tell it method equals bisection. Right? It's the roots package I'm invoking. Output is value. That's my answer. Right? Just that fast. If I would like to see how it converges, sort of like the output from my program over here, I ask it for output equals sequence. Right? And it, from 0.5, 0.8, it goes 0.5, 0.65, and you quickly see how it converges to that 0.6025 and 0.60224. So I know at least 3 decimal places right there, I'm at 0.602, right, for this answer. And I can see it converge. If I would like to see it graphically converge, I ask for output as plot. And I like the stopping criteria to be absolute error for this thing. And if you want to see the information of how it's converging, the actual steps, like if you were going to do this by hand and do the calculation, plus the error value, the actual error value that it's generating, I ask it for information. Output equals information. Notice I had to change to 10 to the minus third here. If I do 10 to the minus 4, the matrix is too big, and it will not output it for me. It doesn't like to do that. I would have to change some of the base configuration inside Maple to get it to do that. I just want to see the thing converge, right? So I just left it and changed it from 10 to the minus 4, 10 to the minus third. There's a different way of calling this. You can also call it by bisection. It does give that. Notice you get almost exactly the same answer, but notice it's 0.60228. This is 0.6023. All right, so it rounded up what was above. Notice that I changed the stopping criteria down here, though, to absolute. You will get a different answer if you have relative stopping criteria and absolute stopping criteria. I think absolute is better. That's why I use it. This, again, gives me bisection down to an output for a sequence. The plots look exactly the same. The information looks exactly the same. And then I went ahead and did another function. Here I just did a cubic. It's 3x cubed minus 4x squared plus x minus 1. Again, I only had 1 0, right? And that's between x equal to 1 and x equal to 1.5. And it converges rather nicely. Right? So you can take a look at those. Remember, there's Math Player. From the Maple Player, I'm sorry, from the MapleSoft website, which is free. You can load any of these, and you could actually get to see it happen if you want to take a look at it. This false position method, I started with the same functions, and I tried to do this. Notice it's not really cut out to do this. Stopping criteria is not met. It can't do this thing. If I try and do false position and tell it even 10 to the 5th maximum iterations, it runs out of iterations before it gets there. This thing is converging so slowly that it is just tragic, and it's not going to give you a good answer. The same thing happens for just that simple cubic. It does terrible things. I have to admit that I, just for giggles, because I really want to know if it would ever converge, I boosted this max iterations to 10 to the 9th and let it run overnight, and it still didn't do what I wanted it to do. So it takes quite a while, and it doesn't give you good results. Right? So I don't like false position at all. You notice there's no false position homework. Fixed point iteration does give me an answer. It doesn't converge nicely. You know, the answer should be 0.6. This is 0.59. So I'm not getting good results. And, you know, if I try to up the max number of iterations, and notice this was a tolerance of 10 to negative 2. If I go to tolerance 10 to negative 4, I have to up the number of iterations to something ridiculous and then let it run basically overnight. Right, so fixed point iteration, not the way to go either. Notice how slowly this is converging. Look at how slowly the absolute error is going down for this thing. It's not worth it. It's not going to give you fast convergence, even for that crummy cubic. Notice this thing diverges. I gave it good criteria, right? It's, you know, x equal to 1.2, right? And it's not able to get there. All right, so again, fixed point and false position, not something we want to do. Newton-Raphson, of course, we know that works. And we know that works very, very well and converges very, very quickly. So that's, you know, thank goodness. You finally breathe a sigh of relief. You know, look how fast the absolute error goes. You don't even have to get to the max number of iterations for this thing. Right? 4 iterations, basically 3 after the initial point, and we're done. I go out to that cubic, and for the cubic, I have to go out to a whacking great 5 numbers of iterations before it converges. Again, very, very fast, very, very good. I know what the book says, that Newton-Raphson does this, that, and the other thing. Yes, if you have 2 zeros close to each other and you pick a bad starting point, it can hop between the 2 zeros. This is why you graph it first. Right? Graph it and then pick a value. If you want the right-hand 0, pick a number closer to the right-hand one. If you want a left-hand, pick the number closer to the left-hand one. Yeah, it will work for you in most cases. 90% of the time, Newton-Raphson will work. I don't know what the book was whinging on about. Secant method also works very well. I like that. It takes more iterations to get to where we want to go with the secant method, but it definitely will get there. And it does a beautiful job with the cubic. It takes one more iteration with the cubic than Newton-Raphson. So if you don't like Newton-Raphson, go ahead and use secant. Secant will work just fine for you. The modified Newton-Raphson, of course, if Newton-Raphson worked, modified Newton-Raphson should work. It takes one more iteration, though, for this first one to do modified than it does to do the standard. And for the cubic, it takes the same number of iterations to get there. It doesn't converge any quicker. So I'm not... and again, you can either call it by modified Newton or you could call it by roots method equals modified Newton to be able to do the solution. The last one is Stephenson's method. And Stephenson's method is based on a version of Aitken's delta squared technique. There is a reference to that in the book, and you can find it, online. I even gave you the link to Wikipedia. I am not a huge Wikipedia fan, but at least, if you want to look this up and get the basics for it, it does converge very, very well. And notice that, 5 iterations and we're there, and it gives a very good absolute error, gives very good numbers, numeric values, even for the cubic. The cubic does converge very quickly. So I also recommend Stephenson's method. These things run that fast, quite honestly, that you could run all of them all the ones that not false position and not fixed point. All right, let's just get rid of those. All right, but bisection, Newton-Raphson, secant, you could pick 2 of these and run them on the same exact function, and it will give you the answer that you are looking for. All right, so that you can get